Welcome back. We're going to start chapter 17 in this video, which is sampling distributions. So in the last class or the last chapter, chapter 5, we had questions like this, right? Where we wanted to calculate the probability that a single person would have an IQ score of 85 or less, given that the mean IQ is 100 and the standard deviation is 10, right? And that these IQ scores are also normally distributed. It's pretty important. So what would we do to solve this? Well, we would find a z-score, right? We would plug in the x value of interest, right? Here, we wanted to find the probability of a person having an IQ score of 85, right, or less. So that's where that 85 comes from. We'd subtract our mean of 100 and divide by the standard deviation, which was 10. That would give us our z-score, right? In this case, it would be negative 1.5, shown right here, right? And we'd be looking for that area under the curve to the left of negative 1.5. We could look this value up in a z-table, right, to get the area under the curve, or we could use our TI-84 calculator, use the normal CDF function. This should be a positive 100, not a negative. Right, but we could use the CDF to get the area under the curve, which would be 0.0668 or about 6.7%. But what if we want to calculate the probability that 4 people would have an average IQ score of 85 or less, given that it's normally distributed, right, with a mean IQ score of 100 and a standard deviation of 10. So notice the difference here, right? Before we were talking about one single person, right, having one single IQ score of 85 or less. Now we want to know the probability that 4 different people, if you take their 4 different IQ scores, right, add them all up, divide them by 4 in this case, the sample size, what's the probability that that average score would be 85 or less? Think about this for a second. That's kind of harder to do, right? Do you think it's harder to pick one person out and just see what their single IQ score would be, you know, given some criteria, whether it's 85 or 90 or whatever, or do you think it's harder to pick 4 people, take their average, and make sure that average is a certain score or less? Kind of think about that, keep it in the back of your mind, and we'll talk about it later. So we're now taking a sample, right, and averaging the data from that sample, i.e. sampling distribution. In this case, it's of the sample mean, right, because we're taking a sample mean or a sample average. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So remember, a statistic is something that comes from a sample. And what we're saying here is, for our population, if we could sample it over and over and over again, hundreds of times, thousands of times, if we were to take different samples from the same population, each one of those samples would end up having a different mean, right? A different average. If I'm in your sample one time, my IQ score will affect that mean. But if I don't make it in your second sample, well, you don't have my IQ score, you have someone else's, right? That's probably a lot bigger than mine. And you'll get a different mean, right? Most likely. Could be the exact same, but it'll most likely be different. And so you take all of those sample means possible and you plot them and make a distribution out of those. sample means. So to understand how our graph will be different, we need to understand the central limit theorem, right? So what is this new distribution of these sample means? What is it going to look like? Will it be normal? Will it be bimodal? Will it be multimodal? Will it have a hump at all, right? What's it going to look like? So the central limit theorem says the sampling distribution of the mean will always be normally distributed regardless of the population distribution that it comes from, as long as certain assumptions and conditions are met. So this is really powerful, right? No matter what population we're looking at, no matter how that population is distributed, whether it's normal or not, if we take samples after sample after sample from any population, and we take the mean of each of those samples and we plot those sample means out, they will be normally distributed. Here are those assumptions that we need. We need an independence assumption. The sampled values must be independent from one another. They can't rely on each other or be dependent on each other at all. We have a sample size assumption. The sample size must be sufficiently large, right? If we take 2 samples, it's probably not going to look normally distributed, right? We need to take enough samples so that we start to get a normal distribution. The randomization condition says the data values must be sampled randomly, and something called the 10% condition. When the sample is drawn without replacement, which is usually the case, the sample size should be no more than 10% of the population. So if my population is only 1,000 people, then my sample size shouldn't be 10% of that. Shouldn't be equal to 100 or more in that case. I'd only be able to come up with 10 samples, and I would have sampled my whole population by then. So the sampling distribution of the mean basically says that if you have a simple random sample and a sufficiently large sample size, usually we take n greater than or equal to 30, and a finite population standard deviation, basically saying that your standard deviation is a number, then your sample means will have an approximately normal distribution. And the greater the sample size, the closer the corresponding X bars or sample mean distribution resembles a normal distribution. A simple random sample used to obtain X bar, probably a sample mean, provides an unbiased estimator of our population mean. So in other words, the mean of the sampling distribution of those X bar values, the sample means, is actually our population mean. And this is really, really powerful, right? So we've taken a bunch of samples, right? For each of those samples, we've taken a mean, and then we've plotted all of those different sample means, and we've said that they look normally distributed. They are normally distributed. So at the center of our sample mean distribution, right, is our mean of those sample means. And basically what this is saying is if you average out all of those sample means, if you take the average of all of them, that will be equal to your population mean. So this is really, really powerful. Obviously in statistics, right, the idea is you take a sample or samples, right, you get statistics out of that, and you want your statistics to tell you about your entire population. And that's exactly what this is doing for us here. So basically in notation, this is just that the population mean, right? If you could take all the samples possible, right? The population mean of all of your individual sample means is equal to the population mean from the distribution you started with. And don't worry, we're gonna do a separate video with a little bit of a kind of an illustration or not necessarily a problem example, but a simulator that'll kind of hopefully make this make a little more sense if it's not making sense yet. Um, so that's great. And then the variance of those sample means will be equal to the population's variance, but it's divided by our sample size, right? So the variance of our means is not directly equal to our original population variance like the mean is. We have to divide it by the sample size. And so this means the standard deviation of x bar, right? You just take the square root of this. So that square goes away. So it's equal to the population standard deviation over the square root of n. So we can basically summarize this and say our sample means are normally distributed with a mean or a center, right, of our population mean that we start with, and variance divided by n. A variance, sorry, of the population variance divided by our sample size. So this slide kind of tries to illustrate that point. Again, I'll do another kind of video on showing this, but basically think about this example where you toss one die 10,000 times, and every time you record the value, right? So you can have a 1, 2, 3, 4, 5, or 6, right? 6-sided die. You toss it 10,000 times, and it's a fair die, right? So you get about 1,500 of the 1,500 ones, 1,500 twos, 1,500 threes, and so on, right? You would expect to get about the same number each time, right? But now let's take 2 dice. Okay, let's roll those 2 dice 10,000 times. And every time we roll 2 dice, we take their average, right? This is like taking a sample of 2, right? Our 2 dice are a sample size of 2. And we're taking 10, we're doing that 10,000 times, right? And each time we're taking the average. And this is what that looks like if you just take the average of 2 dice and you plot it 10,000 times. See how this starts to look normal already? It's already unimodal. It's already symmetric, right? And then if you do that with 5 dice, it starts to look like this, right? We start to get a little bit more of a curve. Looks even more normally distributed. And then if you do it with 20 dice, so a sample size of 20, look how normally distributed that looks with those. So we take with those averages, right? So we've taken 20 dice, rolled it one time, taken the average of that 20, right? Plotted it once and done that process 10,000 times, basically. So basically for larger and larger sample size n, we expect the sampling distribution's shape to become more normal, more unimodal and symmetric. The center will stay the same and the spread will become smaller. So this was important too, right? The average here never changes, right? Our scale doesn't change. It's still centered around 3.5 or so, right? It keeps getting closer and closer actually to that 3.5 average, which makes sense, right? If you take 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, that average is actually 3.5, right? So for this dice example, you would expect the average to get closer and closer to 3.5, which you can see it does. And then you can see the spread of the data is getting smaller and smaller. Right here, our 10,000 rolls are spread out pretty uniformly, right, evenly between all these values. But then as we increase our sample size, the spread becomes smaller and smaller, right? Our data is more concentrated around this 3 to 4 range. And so how much smaller is the spread becoming? Well, it's becoming smaller by dividing it by the square root of n, right? So I'll work through this problem in the next video, and we'll see how these new problems kind of change when we're actually working them out.